everybody, and welcome to another episode of Echo Live. We are here to talk to you today about gravity games. Now, you might know why we are talking about gravity today. Today, there is a really exciting event that is scheduled to take place in just a couple hours. If you know what I'm talking about, go ahead and tell me in the chat. Do you know what's supposed to happen just in a few hours now? It's something that's happening right here in the United States, something super duper exciting. So if you are familiar, go ahead and tell me in the chat. Using the chat feature throughout this program is going to be your way to communicate with us throughout the program. And specifically, it's your way to communicate with our very special guest star, rock star scientist Raul is here to talk to us all about gravity and tell us a little bit more about this really exciting event in American history that's taking place today. So with that, please introduce yourself in the comments. Make sure that we know that you are here. Raul will be able to see those comments. We'll save some time towards the end of the program for questions that you might have about this event or about gravity, all the things Raul is going to talk about. With that, I won't say any more. I will let Raul take it away.
All right. Hello, everybody. Thank you so much for joining me again today. As Anna mentioned, today is a very significant day in the history of space travel, science, physics in general. And I actually want to discuss this for just very briefly before we go into our lesson. So today, the SpaceX, I think it's a demo 2 is going to be launching today. I believe we're going to have a watch party later, so Anna will tell us more about that at the end of the show. And this is going to be the first commercial flight up into Earth's orbit. Now, why is this significant? Well, if successful, this would be a method to help space travel and space science be more accessible to us as regular people, right? So when I was a kid, I used to read books about people going on trips to maybe like Jupiter. Of course, that would not be possible to land on Jupiter because it's made out of gas, right? But like this science fiction, little by little, is becoming science fact. After this, we might have tours in lower Earth orbit. We might be able to maybe take trips close to the ISS. The possibilities are endless if you think about it. So this is going to be super duper cool. Make sure that you guys check that out. And the astronauts are going to be Doug Hurley, and I believe his name is Bob Buchanan. I forgot his name, but check that out. It should be super duper cool. Now, before we talk about today's lesson, I want you all to type in the chat, what is keeping us on the ground right now? What keeps us grounded? Do we have anyone answering that right now? I think I'm starting to see some comments pop up. And it looks like someone said gravity. That's right. That brings me to my second question. What is gravity and how does it affect your life? Now, for most of us, we think about gravity as a force that keeps us on the ground, right? Without it, we would float up into the vacuum of space. And that would not be very good for people like us, right? Because we're made out of mostly water, or water would evaporate in space. It would be super crazy. So it's very important. For rockets to leave, it needs to beat gravity. Now, to beat gravity, well, it's super duper hard. So I want to talk about different ways that we can trick gravity today. I'm going to teach you how to maybe build some of the stuff that I'm making today. So let's go ahead and start. Now, gravity affects our life in many ways, and most of the time we don't even notice it, right? So to think about how it affects just physics in general, I want to go ahead and go to our PowerPoint so we understand some very fundamental physics. So there are 4 interactions that dictate how all particles in the universe work together, how they interact, right? So that is the strong nuclear force, it is the weak force, electromagnetic or electromagnetism, and gravitation. These used to be known as the 4 fundamental forces. Now they're known as the 4 fundamental interactions. So very quickly, the strong force binds the nucleus, keeps it together. Electromagnetism it binds the atom, so it has more to do with the electrons on the outside. Weak force actually helps in radiation, which you can see there in our picture. And gravitation binds the solar system, it binds nebulae, it binds everything in the universe. But what is it? Well, there were two very important scientists that decided to study this, two of my favorite. Number one was Isaac Newton, and he came up with the theory of universal gravitation. And he said that, maybe particles in the universe are attracted to each other because of their mass, right? Okay, well, his theory of universal gravitation helps us, at least locally, but it didn't quite complete the theory of what gravity is, right? So I like to think about it like this. Newton talked about what gravity is. Einstein talked about why gravity even works. So let's go ahead and go on to my next slide there, because I'm about to maybe confuse a lot of you. Guess what? Gravity is not a force. Again, this is why we call it the four fundamental interactions now. The forces you feel when jumping off an elevated space is the upward acceleration of the ground relative to your frame of reference. Now, what in the world does that mean? Are we confused already? Maybe. So let's go ahead and talk about Einstein's happiest thought. And that's going to be on the next slide. So what do I mean by gravity isn't a force? Well, let's pretend that we had an elevator, and this elevator was blocked off it didn't have any windows, it was just dark. All you had inside was a weight and yourself, right? And let's say that we are inside of that on the earth. Well, what are some of the things that we're experiencing? Well, we're probably standing on the ground. The weight is probably on the ground as well. Nothing is floating around, right? And we perceive this as gravity. Now, what if we were in space in that exact same elevator, and this elevator had a rocket underneath the bottom, right? And what if we accelerated that to 9.8 meters per second squared? What would we feel? It would feel the same as gravity here, right? Locally, we would see, so actually, I wanna actually illustrate this. Let's say this is our elevator, right? And this is you. On Earth, you're already there, right? If you jump, you fall. If you're in free fall in space, well, you're floating around. When that starts to move, you're gonna feel the exact same effects. And do we know if we're being accelerated by a rocket? No, because we can't see on the outside. To us, it seems like it's gravity. So that's a really cool principle known as the equivalence principle. Let's go ahead and dive a little bit deeper. So let's go back to our slides. And let's actually go back one. In the chat, one more, sorry. In the chat, tell me, which one do you think is the strongest? Do you think it's the strong force that keeps the nucleus together? Electromagnetism, maybe the weak force, or gravitation? Which one is the strongest? Which one is the weakest? Put that into the chat. All right, do we have any answers for that yet? Which one is the strongest? Pretty sure many of you think that gravitation would probably be the strongest because it's the one that keeps us here, right? Well, let me go ahead and do a test. I have a paper clip here, and I'm going to zoom in just a little bit more. I'm holding this paper clip using my energy, my kinetic energy, right? My energy of movement. And if I drop it, suddenly gravity brings it down. Okay, so that seems like it could be strong, but look at that. I have a magnet. Is it falling now? No. Gravity is actually super duper duper weak. And this is why we see people like us, we're so small, we don't have things orbiting around us, right? So what I did today is I made this really cool device that tricks gravity. Tricks gravity, right? So I tied a paper clip to this string, then another one here, and I put two magnets up there. So if I go ahead and do that, suddenly it seems like we're defying gravity, right? I can even put my finger in there. So this is just more proof that magnetism is much stronger than gravity. Okay, so let's go back to our slides really quick and talk about two other scientists. So there were two people known as Aristotle and Galileo. Galileo, again, is one of my favorite scientists. Aristotle said things fall to the ground based on their mass. Things that have more mass are going to fall faster than things that have less mass. And, you know, at first glance, that seems logical, but then there was this guy called Galileo that said, no, everything falls at a constant rate. The only thing that changes are the forces that are being put on that object. So you'll see on the left two very cool demonstrations of that. So you'll notice we also have on the right a really cool picture from Apollo 15. That is David Scott. Now, David Scott actually proved Galileo right. In a vacuum, gravity, free fall, when things are in free fall, things fall at the exact same time. So I want to go ahead and show you this video. Let's go ahead and bring it up so you can see that proof.
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Joe, you have a good picture there. I've got
Beautiful picture, Dave.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
How about that?
Proves that Mr. Galileo was correct in his findings.
Superb. Jim.
All right, super cool stuff, actual footage from the moon. Now, on the moon, we have a nearly perfect vacuum, right? We actually have conducted this test. I believe it was in Cleveland. They have a giant vacuum chamber if you all want to YouTube that later, and it works. So I want to go ahead and prove that to you here on Earth. Let me put this down because this might get a little bit intense. So right here, I have a very high mass ball. If I throw it up, I catch it, it's very heavy. This looks like a foosball ball. Not too much, right? I'm gonna go ahead and drop them at the same time. Tell me which one fell down first. Ready? 1, 2, 3. One more time. 1, 2, 3. Right, so after those two trials, what did you notice? They both fell down at the same time, at the same constant rate. So what if I wanted to use this? So this is just a regular shopping bag, and I drop them both at the same time. What's going to happen to them? Go ahead and type that into the chat. And if you are reading any of the comments on the chat, I can't hear you, Anna, just in case.
Have not just yet, but I will let you know when they start to kind of flow in. People are starting to respond, and they understand that both of the balls were falling at the same rate, We're still waiting for some answers to come in about your bag versus the ball. And could you explain one more time, what is different here than on the moon? Why does this relate to that video we watched?
That's exactly where I'm going with this experiment. Remember that on our planet we have an atmosphere. We have gases in there. And this has a lot of surface area. And, you know, it's not very dense. It's not very massive. And if I drop this at the same time, unlike the moon, of course, this is going to fall first. But what's keeping this from falling at the same rate, at least here on the planet? Well, let's think about the atmosphere. All of that is creating drag. It's creating resistance. And that's why this falls after this thing falls. If we were on the moon or in a perfect vacuum, like we said in Cleveland, they would both fall at the exact same time, as was proven in that video. Super duper cool. So can we use air resistance to trick gravity? Well, that brings me to my next experiment. This is actually one of my favorites. And basically all this thing is a mason jar, a little bit of cloth. It's like cheesecloth, a little more fine, I guess, and a rubber band holding it down. So this is very tight, almost like a drum, right? Now I'm going to go ahead and pour all of this water in there. As you can see, this thing has a lot of holes, very porous, so the water goes straight in there. Now you'll notice I didn't fill it up all the way. There's still a little bit of air in there, right? I'm going to go ahead and cover it with this card, flip it over, and in the chat, I want you to form a hypothesis. When I remove my hand, what is going to happen to that card? Is gravity going to make this thing fall, or is something else going to happen? Well, let's go ahead and gently let go. What do we notice now? Well, that card is still on there. Okay, that's fair. Maybe there's some really cool science going on, right? What if I took that card out? What would happen to that water? Do you think it'll fall out? Type that into the chat. Well, I'm going to very gently remove it to see what happens. Oh, what do you know? That water is still stuck in there. Now, this isn't magic. This is basically the same science we talked about. So in this case, we're using the effects of the cohesion of water and air pressure to keep that water in there. So that is stronger than gravity as well. So what's happening here is that all that water is sticking down here. And because of water tension on these little holes, it doesn't fall out. Another thing that we did is when we flipped it over, all of that air went up here. So we created a tiny vacuum in there. And if we were to break this, well, all that water starts to finally pour out. Or if I just tip it over. This is a fun one to do at home. Ask for your parents' permission. And as you could see, I had a little thing here to catch all the water so that my desk doesn't get all wet. Okay, so now that we know that gravity is affected by either the atmosphere, it's affected by factors such as the acceleration of bodies, what if we were a small little ant and we wanted to travel from one place to another on a planet? And you know what? Today I brought my BB-8 droid. Gonna take off his head. We'll be fine. We're gonna use his body as a planet. And let's say this is the Earth. Now the Earth is actually a little bit more oblong at the center because it is rotating, right? And well, what do you know? I also have a little ant here. Let's get a little bit closer so you can see that. A little tiny ant, and he's going to follow this dotted path. So we know gravity isn't a force, right? What is gravity then? Well, gravity is just the effect of curvature of space-time. Now, what does that even mean? Before I confuse you with that, let's talk about dimensions really quick. So this is a two-dimensional ant. This ant can travel up, forward, backward, left and right. It cannot travel up and down. So that would be at you and at me, right? That would make it a three-dimensional thing. like us. So if this ant travels that straight line on the planet, it's not going to be able to perceive that as it travels in that straight line, the planet is actually curved, right? So using this same logic, we can apply that to the rest of the universe, except that our universe is four-dimensional. You can think of the fourth dimension as time, since we have all directions covered in the first three dimensions. And I want to actually show you how that works. It's a really neat device that you can make at home as well. It's called a gravity well. Now, there we go. This gravity well represents the fabric of space-time. Now, remember, this is only a three-dimensional representation of what's going on. Space is four-dimensional. It's all over and it includes time. But this is really helpful for showing you one of Einstein's ideas known as general relativity. So let me do that again. Notice when I add a lot of mass to that, space-time is warped. So again, much like my ant, if I want to travel in a straight line like that, but I'm caught in the curve of space-time, what's going to happen? Well, I'm technically still traveling in a straight line, but I'm just following the curvature of space. If we had a grid on here, perfectly illustrating points that we could put on there, you would still be traveling on that straight line. It's pretty brilliant. And we can actually represent orbits on here, as you can see. We can represent the solar system. So let's say I had a slightly bigger marble than this one, right? Now, if we say this is the sun, this is the earth, and this is the moon, do you think that the same effect is going to happen for them? Do you think that as the earth travels around the sun, the moon would then travel around the earth on this model? Absolutely, it does. Check this out. Really beautiful. Now, things in the universe like to travel in straight lines. My old professors used to call it the law of cosmic laziness. So what if we removed the sun from the middle? Well, suddenly they would start traveling in a straight line to wherever they were going. Really cool experiment, right? Now, there are other objects in space that make space-time interact differently too. If we have a point that is infinitely dense, like a black hole, well, that rips through space-time, right? If we had a repelling force, like that, well, that represents dark energy. What is dark energy? We really don't know. So maybe one of you will be the person that discovers that in the future. Now, I know a lot of this is really, really complicated, but it's a really great start. I would recommend that you start reading about Einstein and Newton. I want to go ahead and take these last 5 minutes for questions, though, because I know this can be pretty complicated, and I want you to understand what gravity is.
Absolutely. So if you have questions for Raul, go ahead and type those in the chat. We'll come back to those. And while we wait for your questions to come in, I'm sure you've got them. Raul would love to answer them. Let's talk a little bit more about that launch. So the launch today is scheduled for 4:33 p.m. Eastern time. So where we live here in Michigan and down in Florida, it's 4:33 p.m. Eastern. And so there are all sorts of live streams happening. They've been going on since about noon today. You can watch the crew getting prepped and ready. The astronauts are actually in the launch capsule right now. The door has not yet closed, but it will be closing soon, which is a good sign because that means that the launch is scheduled to proceed as planned. A little bit later today, we are going to host a watch party on the Michigan Science Center Facebook page where we can actually watch the launch all together. Our NASA Solar System Ambassador, Paulette, is actually going to help moderate that live stream. She can talk to us a little bit about her insider knowledge from NASA, which is super amazing and cool. But she can also answer your questions about the launch. And even if there is a reason that for some reason the launch has to be scrubbed today, we will talk about why that is, and we'll connect, and they should be explaining that on the live stream as well. But to give you just a little bit of a heads up about that, there are so many reasons why this launch could be scrubbed. There are 11 weather criteria, and each one of these really amazingly complicated criteria. If one of them is applicable, something, if the winds are too fast, or if there are lightning strikes within 10 nautical miles of the launch pad, if even just one of any of these weather criteria are met, we would have to scrub the launch because, like Raul said, this is the first commercial launch of NASA astronauts, and it's the first launch happening on United States soil in almost 10 years. And so we, of course, NASA wants to protect the safety of their astronauts above all else. So we are, of course, hoping that the weather will turn out in our favor, that we don't meet any of those criteria that would cause us to cancel the launch or scrub the launch, as we would say. But hopefully we'll get to launch at 4:30. If not, the next window is actually this Saturday afternoon. And so it won't be too far off if we can't launch today. It will only just be a couple more days that we have to wait. So let's see if we got any questions while we were waiting, Raul.
One more note. The name was
ahead.
Bob Benkin, actually.
Oh, yeah,
and
yeah,
Doug Hurley,
exactly.
yeah.
So a
Questions?
couple of people are asking about G's, G forces, really. What are G forces and how does that relate to gravity?
G forces are dependent on the mass of an object. So just like we saw in the gravity well, if we have a higher mass object like this, its G forces are going to be much, much stronger. It's just how strong the gravity is on that planet. And if we were to go to the moon, well, it would be a lot more different, right? Because the moon is much smaller, it doesn't have an atmosphere, so you would actually weigh less on there. If you were to go to Jupiter or something, you'd even more, right? That's basically how that works in most simplest terms. Any other questions?
Yeah, a couple of people are asking, so our watch party for the launch today, we're going to start it at 4 o'clock, and that should give everyone enough time to join in, talk to Paulette a little bit before the launch is scheduled to take place at 4:33. The interesting thing about this launch is they have an instantaneous launch window, which means that if it cannot launch at 4:33, we can't push it back by a few minutes. We can't push it back by a couple hours. Like we said, the next window will be on Saturday. And so we should know at that point whether or not the astronauts will be launching. So we'll start the watch party at about 4 o'clock. Their only place we'll be streaming this live is on the Michigan Science Center, or the watch party will only take place on the Michigan Science Center's Facebook page, because that's the way we're able to host a watch party. So please try and join in through there. If you can't find it, we will still post links for you to find it. If you look up NASA TV, they've got the launch streaming on all their platforms as well. So you can watch it on NASA's YouTube channel, on the NASA TV website. So if you're not able to join us on Facebook, I know some people don't access our Echo Live programs on Facebook. If you're not able to, you will still be able to watch the launch if it's not scrubbed later today. Let's go ahead and see if we've got any last questions. Mostly talking about the launch, lots of people super excited, and I'm hoping more excited than before the program, because now we understand just how much physics and engineering has to go into these types of launches because of these forces of gravity, right? So we will be posting activity guides for some of the activities that Raul showed today. There is one for how you can make your own gravity well, which is that stretchy black fabric. If you don't have those materials at home, we have a way that you can actually create one by standing on your own bed. If you stand in the center of a mattress, you can do something very similar and do some of those exact same experiments that Raul did. Those will all, of course, go on the Michigan Science Center's website, as always. So if you are looking for at-home experiment guides, visit the Michigan Science Center's website /@home-science. That's where you can find those. If you enjoyed this program, we hope that you will like this video, share this video, and we hope we'll see you back here at about 4 o'clock for the watch party for the SpaceX launch. If not, we will see you back here tomorrow for another episode of Echo Live on a whole different topic. And hopefully we'll have some amazing news to share about how the launch went. So with that, thank you so much, Raul, for joining us, and we will see you back here.